This is Dr. Wortel with a revision video on proving non-existence of a limit, so proving that a limit does not exist. So what the goal in this video is to prove a statement like the statement in red here. I would like to prove that the limit of fxy, where the xy goes to the point AB, does not exist. And often we want to use theorem 45 for this. Okay, so theorem 45 involves two different paths. So let us just make a little picture to understand what this theorem is saying. Okay, so I have my point AB somewhere in the plane. Let's say it's over here. Okay, and there's two paths involved, R1 and R2. So let me just draw some paths that go through the points, like this, a blue path and a green path. So let's say the blue path is R1 of t, and the green path is R2 of t. Now there are some conditions on these paths that are here, but basically what they mean is that these paths should only cross the point AB once. Well, actually only in a small neighborhood of this point where t equals c, but this is how we will use it in practice. So the path should only go through the point AB once. Okay. Now what we can do is we can compute the limit of fxy not where xy goes to AB, but we can compute it along this path R1 of t. Note that this will be easier because we now have a single variable limit instead, and we can use the techniques from the first year. Okay, so there are two possibilities here. And the first possibility is that if we compute the limit along, say, one of these paths, R1 or R2, we could find that the limit does not exist along one of these paths, R1 or R2. And in this case, using part 1 of theorem 45, we can immediately conclude the red statement that the limit for xy going to AB of fxy does not exist. And remember, that's what we want. So that is one possible application of theorem 45 in the proving the non-existence of the limits. The other possibility is that both paths, limits along both of the paths do exist, but they could be different. For example, the limit along the blue path could be 4, and the limit along the green path could be 7. And this is part 2 of the theorem, which states that, oh well, if the limits exist but are both different, then we can also conclude that the limit for xy going to AB of fxy does not exist. And so there are two possibilities where we can use this theorem in order to prove the non-existence of the limits. Okay, so now how does this work in practice? So let us consider the case where we want to prove, that the limit for xy to, let's say, the origin of fxy does not exist. Let's say we are asked to prove this. Okay, so let's make a picture of this case. So now we have our point AB is now the origin. Now note that no paths are given, so we should think of paths ourselves. So the question is, well, which path should we choose? And here comes, I guess, the difficulty. But it makes sense to choose easiest path, because that's going to make the computation of the single variable limit easier. Well, what is the easiest path that we can choose? Well, we could say go along the x-axis, right? So that will be the blue path. Let's call that R1 of t. R1 of t, which is in this case the x variable is t, and we can see that the y variable is 0. So this will be easy to compute because you just take your function fxy, you substitute for x, you substitute t, and for y you substitute 0. So that's sort of the easiest thing we can do. Okay, so we need two paths. So another path that is very easy is along the y-axis. So let's also take that one. So R2 of t, which is, well, in this case the x-coordinate is 0 and the y-coordinate is t. Note that both these paths satisfy the requirement that they only cross the origin when t is 0. Okay, so you could consider those two paths. And now you could compute this limit along both of the blue and the green paths. Okay, so as I said before, suppose one of the limits does not exist along one of these two paths, then we are immediately done, because then we conclude that the limit does not exist. So another possibility is that both limits exist and are different, and then, as I said before, we can also use theorem 45 to conclude that the limit does not exist. So then we are done. Okay, but it will not always be so easy, because sometimes it will be the case that the limits along the blue and along the green paths exist, and they could be equal. And in this case, we cannot apply part 2 of the theorem. So the question now is, what to do if they are equal? And the answer is, well, let's look for more paths. Maybe it doesn't work if we go along the axis, but maybe we should take a slightly more complicated path. So one thing that we could do is, for instance, go like this. Right? We could take R3, which is the path TT, and it also only crosses the origin for t is 0. So that also satisfies the requirements. Now, if if the limits for R1 and R2 are the same, hopefully the limit for R3 may be different, and then again we can apply part 2 of theorem 45. Now with R1 and R3, if R1 and R3 are different. Yeah, so that's one thing one can do. However, again, it can happen that this limit could be the same, and then I guess we have to get a bit creative and think of other paths. So one possibility that you could do is, instead of going in a straight line, we could go in a paraboloid path. So for instance, we could go like this. Right? Let's call this R4 of t. Now think of yourself how to parameterize such a paraboloid. But when this happens, you have to get creative and you have to find a good path, and hopefully at some point you find a path for which the limit will actually be different or does not exist, in which case we can use part 1. And if it is different than any of the other paths, we can use part 2. Okay, so what I would like you to do is now to use these techniques that I just sketched and to do this exercise. So show that the limit for xy to the origin of this function x squared y squared over x to the third plus y to the sixth does not exist. So please try it using the paths that I suggested in the previous slide. And then please pause the video, and then I will give you the answer afterwards in the second part of this video. Again, I want to stress that it is really important that you actually pause the video and actually attempt this yourself. Otherwise, it will lose much of its effectiveness. So please try this yourself, and I will be back soon with the answer. So for the solution, let us consider first the path R1 of t, t0, t0. Okay, so let's first check the conditions. Well, firstly, note that this one is continuous. It hits the origin exactly when t is 0. And if t is not 0, then it is not the origin, right? Those are the requirements. If t is not 0. Okay. So now let's compute the limit for t to 0 of f of R1 of t. Okay, so what do? We take our function, which is x squared y squared over x to the third y to the sixth, and we substitute. Maybe I should do one extra step. So R1 of t is t0. So I substitute for xt and for y 0. So what do I get? I will get t squared times 0. So I get 0. And in the denominator I get t to the third. Okay, well 0 over t to the third when taking this limit is just 0. And the limit of a constant is just the same constant. So the limit along this path, along the x-axis, is 0. Yeah, so again, let's make a little picture. If we go along the x-axis, we get 0. Okay, so now, well, in the previous picture we went along the y-axis, but it's very easy to see with a very similar computation that if we go along the y-axis, the limit will also be 0. And that does not help us, as I explained before, because we would like to find two paths with different limits. Yeah? So please check yourself that if you go along the y-axis, you also get 0. So let's try this the third path, or well, okay, let's call it R3. Let's try the path TT that I suggested in the first part of this video. Okay, so let's think about R3 of t, which is tt. Okay, we need to check the conditions, but clearly this is continuous. Both components are continuous. It's the origin at 0, and R3 of t is not equal to 0 if t is not equal to 0. So it only hits the origin when t is 0, so that is fine. Okay, so that satisfies the conclusions. And now let's compute the limit for t to 0 of f of R3 of t, which is the limit. Okay, we'll skip a step here. So I have to plug for x and y both t. So what I get t to the 4th, and I get t to the 3rd plus t to the 6th. Okay, well, we can see that there's a common factor t to the 3rd in both the numerator and the denominator. So I can cancel those, because when taking the limit for t to 0, t is never 0. So I can take out a factor t to the 3rd over t to the 3rd, and that is equal to 1. So then we get t over 1 plus t to the 3rd. Well, this is now a continuous function in t, also in 0, so we can just plug in t as 0 here. And this will give us the limit. Yeah, so we can plug in 0, so we get 0 over 1, which is again 0. So again, we are unlucky, and we see that again, if we go along the red path, the limit will also be 0. So we already checked the blue, I didn't check the green, but you can do that yourself. Along all 3 of these curves, we get a limit of 0 now. Okay, so now you can take this paraboloid that I suggested, but actually let's think a little bit about this function. Well, we have x to the 3rd and y to the 6th here, and it's maybe better if these sort of become a similar power after I plug in some t's. So maybe x should be t squared and y should be t, and because then I've got t to the 6th in the denominator, and that looks nicer. So that's just my motivation for going for this path. So let's call this R4. So this is, what did I say? X is t squared and y is t. Well, then again, I check the same thing. R4 is continuous. R4 in 0 is the origin. And R4 is not equal to the origin if t is not equal to 0. Okay. And now let's compute the limit for t to 0 of f of R4 of t. So maybe I should make a picture. So that's going to look roughly like this. So this is going to be R4. But yeah, that doesn't matter. Okay, what happens if we compute this limit? Okay, so for x I have to plug in t squared, and for y I have to plug in t. So I get t to the 4th times t squared in the numerator, and the denominator I get t squared to the 3rd, so that's t to the 6th plus t to the 6th. Okay, so let's compute this a little bit. So I get t to the power 6 over 2t to the power 6. And again, I can take out the factor t to the 6, so I get the limit. I can cancel a factor t to the 6, so I get a limit of a half, and the limit of a constant is that same constant. Okay, and now we are done, because now we found 2 different paths, let's say R1 and R4, with different limits. So let me conclude on the next slide. So now we say, since limit for t to 0 of f of R1 of t is not equal to the limit for t to 0 of f of R4 of t, then let's say, by theorem 45.2, the limit for xy to ab does not exist. Okay, 2 quick remarks is, firstly, let's go back to the previous slide. Here you see that only this and this was necessary, so if you see immediately you have to take these 2 paths, you don't have to take all these intermediate steps, but this is maybe the more logical progression of what you could do. Yeah, but in the end, you only need the path R1 and R4, or R3 and R4, or R2 and R4. You see there are many possibilities.